Economics Magazines. This is the second video of our series in which we discuss the future of flight based on the Economics Magazine's report of May 2019. In this video we will be discussing aircraft construction. Let's get started. Okay, now we look at the process of aircraft manufacturing. Aircraft construction is being transformed is the title and the thesis of the second article. So Boeing and Airbus need to speed up production to meet demand. Okay, so these two names, of course, are the household names of aircraft manufacturing, and we will learn more about them in a moment. We begin with the A350. It's a twin-engined airliner that is the top of the range of Airbus offerings, rolling out of the company's factory in Toulouse, France, at the rate of 10 a month. Each of the finished planes sits at the peak of a system of supply chain which fans out across the world, bringing 3.5 million components together into a single product. Now that is truly amazing. So the supply chain actually brings components from around the world, some 3.5 million components into a single aircraft product. The A350's airframe is composed of 7 sections. 3 are assembled into the fuselage. 2 of these are made in France in another site, not in Toulouse, and the third in Germany. The 2 wings are made in Britain and then transferred to Germany to be finished. The tail fin and the horizontal stabilizer assembly are made in Spain. So let's repeat this time, looking at the aircraft. We are talking about A350. So this is what it looks like with the Turkish flag on it, and an equivalent aircraft is Boeing 787 Dreamliner. So A350 is made in France, Toulouse. The fuselage has 3 parts, the article informs us. They come from different sites in France, and the third come from Germany. The wings are first made in UK, Britain, and then transferred to Germany to be finished and then sent to France. And last, the tail wing and the stabilizers are made in Spain, we learned. So it's Spain, France, Britain, and Germany mainly involved in the production. And at this point I want to show you the Beluga airplane that carries these huge, large components between these countries and finally to France. Let's come back to our article. All these pieces are flown to Toulouse in special transport aircraft that I just showed you, called the Beluga, after the whale, which they resemble, rather than the sturgeon, which they do not. I leave it to you to learn a little more about the Beluga sturgeon at this point. Let's continue. These parts are made mostly of carbon fiber reinforced plastics. So these are composites. These are composite materials that cannot be riveted in the way metal is because of the damage this causes to the fibers. So riveting is the process that we learn about here. So composites cannot be riveted. I will in a moment show you a picture of riveting. They are therefore held together by lock bolts inserted through 10,000 specially drilled holes in the flanges where the sections overlap. We are talking about combining pieces of the fuselage at this point here. So let's look at so these are lock bolts. Basically you drill and then connect this by screwing this way, and this is classical riveting. Where in using metals you can simply do this, push the rivet in and then press it, and everything is done in a single step here. Much easier, but you can't do it with composites, the article tells us, because you will be damaging the fibers and the structure will lose integrity at that point. Coming back. Okay, so a little more discussion about the lock bolts. I'll leave this section to you to read in detail and then continue with the next one. Before their final bonding, however, the fuselage sections have had what are known as monuments, large structures. These are bits of equipment, galleys, the kitchen inside, crew's quarters, and so on, that will be too big to carry through the cabin doors later. Afterwards, the rest of the fitting out is done. The plane is painted in the customer's livery, and the crucial finishing touches, a pair of engines, of course, is required. One under each wing, they are added. The whole process of manufacturing takes about a month. So in a month 3.5 million components are assembled into an A350 aircraft. This is amazing. The whole process takes about a month. Now let's look at the companies that actually built the aircraft. Airbus and American counterpart Boeing dominate civil aviation and have done so for decades. Airbus is the European consortium that builds the Airbus, and we have the American competitor Boeing. Airbus was formed in 2000 though it acquired its current name only in 2014, having previously been known as EADS. Boeing took over McDonnell Douglas, its last American rival in the civil aviation business, in 1997. So these mergers, after the mergers and acquisitions, we have now Airbus and American Boeing. That domination has been enhanced yet further by Airbus's recent absorption of part of the business of Bombardier, a Canadian company, and Boeing's purchase of a large chunk of Embraer, a Brazilian one. So Airbus now owns part of Bombardier, and Boeing purchased a large part of a Brazilian aircraft manufacturing company, Embraer. So therefore we have Boeing and Airbus, basically the two main manufacturers. Besides these two were the last firms in the West with even a nominal claim. We are talking about Bombardier and Embraer here, to be independent makers of airliners. So there is no other manufacturer that can claim to be independent airliner manufacturers. On the other side, a Chinese rival, Comac, may eventually muscle in. They have already produced aircraft, commercial airliners. We will have a chance to look at this aircraft in the future videos. So China is in the game, and the article says in the wreckage that was once Soviet Union, now it is called Russia, of course, the United Aircraft Corporation, a merger of Soviet-era firms, clings to life. So Russia is trying to cling to the game. China is in the game, and then we have but the game is dominated by Airbus and Boeing. But so practically, to all intents and purposes, making airliners is at the moment a duopoly. Okay. So in summary, we have Boeing acquired McDonnell Douglas in 1997, and lately it has also joined Brazil's Embraer and Airbus together with the Canadian airliner Bombardier are both Bombardier, and therefore Boeing and Airbus dominates the market, and we have China's Comac, and can also say include the Russia United Aircraft Corporation as the biggest manufacturers. Okay. Let's the next paragraph discusses the politics between these aircraft manufacturing companies, the cockade nature of Airbus's supply chain. It is distributed uneven chain spread across much of Western Europe, might be seen as a consequence of the firm's multinational antecedents and the desire not to put noses out of joint by politically awkward closures of peripheral plants. So politics, European Union, the connectedness of Europe, all affect the operation of Airbus and its history. It's a European consortium. But we learn that Boeing is no better. The supply chain, for example, for its 787 Dreamliner, the equivalent aircraft, a competitor of the A350, is even more convoluted than for the A350s as a result of a decision early in the plane's history to outsource manufacturing of airframe sections to other firms. So there are subcontractors producing the airframe of the aircraft. So these can be called self-indulgences, inefficiencies in the aircraft manufacturing business. However, there is very stiff competition between these companies, fierce competition. The jurisdictions in which they operate are each acutely aware of any dirty tricks by the authorities in the other intended to support the home team, and are willing to challenge such arrangements in the World Trade Organization. So in other words, these companies are subject to World Trade Organization rules, agreements, and they are not supposed to get state help, so that they shouldn't practice uncompetitive trade practices. And all this helps drive technological improvements. This is the idea of free trade, of course. Okay, let's go back to the airframe discussion again. So what innovations are taking place in the airframe construction? The biggest technological shift going on is an invisible one from metal alloys to composite materials, mostly carbon fiber reinforced plastics. The A350's airframe is 53% composite. The resulting lighter weight, Airbus claims, makes it 25% more efficient in terms of fuel consumption than the planes before. That is a huge saving for the world's airlines, that 25%, because according to IATA, an industry body, fuel accounts for almost a quarter of airlines' operating expenses. In total, $180 billion in 2018. So this is a quarter of airlines' operating expenses. Okay. Boeing naturally matches these claims with its own claims. The Dreamliner is 50% composite compared to 53% of Airbus, and again around 20% more efficient than its predecessors. Composites bring advantages beyond lightness. Unlike metals, they do not corrode. You will remember this from your material science classes. Corrosion, chemical activity that degrade the strength of materials, nor do they crack from metal fatigue. So no corrosion, no fatigue. They therefore need less maintenance. However, they also bring problems. One is that damage to them is less obvious than to metals because they do not bend or dent. This is one reason why Airbus fits hundreds of sensors ranging from voltage meters to strain gauges all over its A350s. These can warn of problems invisible to the eye, so the sensors are always watching the integrity and the strength of the structure constantly. Another disadvantage of composites is that they are not as malleable as metals. So you cannot shape them. They are not as plastic as metals. The paragraph concludes, bit by bit, however, that disadvantage is disappearing. Okay. So slowly it's disappearing. Bit by bit also is an allusion, I guess, to the sensors, to the IT aspect of watching the composites there. If we want to have a look at the composite manufacturing in more detail, this paragraph will help us with that. Parts made of composites are constructed by a process called laying up. This builds a component from ribbons or small sheets of carbon fiber fabric applied to a forming mold together with a resin that hardens when the whole thing is baked in an autoclave. I have a YouTube video in the presentation that you can watch to learn more about laying up and this process in detail. And you should be familiar with the process from your materials classes also. Originally, laying up was done by hand. Then automatic tape laying machines made things faster and more reliable. These days, methods have improved still further. Giant looms are used to weave carbon fiber ribbons into huge sheets. These looms can vary the tension in warp and weft in a way that does the job of the forming mold, creating sheets that reflect from the start the shape of the component of which they will become part. This makes laying up much easier, speeding up production even more. Now this is a truly innovative process in which uh, basically the looms are setting the fibers so that they will automatically take shape of a mold once they are uh, uh, once they are let loose. This is automatic laying and automatic shaping, so you wouldn't need a mold to be able to shape the end product. At this point, I would like to invite you to think about how to shape carbon fiber sheets by giving them some tensions so that you build them in 2D, and then the tensions will warp them into a 3D shape. Please let me know if you are interested in pursuing this topic further, so we can perhaps do a Python program to simulate this 2D laying up with tension, and then it automatically warps into the desired 3D shape. Okay. Please have a look at these two YouTube videos about automatic laying up machines and the more standard manual laying of composite frames. Now let's have a look at the manufacturing trade with a larger perspective. In civil aviation, speeding up of production is going to be crucial. Why? Because Airbus, for example, forecasts that air traffic will grow at 4.4% a year over the next 2 decades, requiring some 36,000 new passenger and 830 cargo aircraft at a total value of $5.8 trillion. Boeing's forecasts are more bullish. They predict 4.7% annual growth, more than 41,000 new aircraft, and a total value of $6.1 trillion. So, to summarize it, let's say the civil aviation traffic is expected to increase more than 4% annually for the next 20 years. That means 40,000 nearly new aircraft, airliners. As an exercise, I ask you to calculate if air traffic grows by 4% in 20 years, how much does it grow? Coming back. So this is a really fast growth. To meet such demand, both firms will need to up their game, and they are doing so. In other words, increase their manufacturing, make their processes more efficient, and manufacture more aircrafts in the same time span. Oliver Wyman, a consultancy, said in a report last year that it expected production of Airbus's A320 and Boeing's 737 each to jump from around 40 a month in 2015 to 60 a month this year. So 50% increase in 3 years. Those figures may need to be adjusted a bit after the recent 373 accidents, but the trend is clear. So these companies are speeding up their processes. And of course, this can bring in mistakes, other problems, stresses of all kinds to the production process. Let's have a look at this visual here. The World Takes Flight is the title. Global aircraft fleet. In 2018, we are talking about 20,000 aircraft. And in 2037, we are talking about from 20,000 to 50,000. So an additional 30,000 aircraft. And so basically it's the double. The fleet is more than expected to more than double in the next 20 years. We are not finished with the manufacturing yet. We will continue this topic in the next video.